Welcome to our video, where we explore the exciting world of artificial intelligence. From advancements in machine learning to the latest developments in natural language processing, we'll take a closer look at how AI is shaping our world. As you watch, remember to subscribe and like our video to support our efforts in bringing you the latest and greatest in AI research and development. Your support helps us continue to create cutting-edge content and make the most of the technology of the future. So sit back, relax, and enjoy the show. Reinforcement learning, RL, is a type of machine learning where an agent learns to make decisions by interacting with its environment in order to maximize a reward signal. RL algorithms differ from supervised and unsupervised learning algorithms in that the learning process is driven by the agent's experiences, rather than a set of labeled examples. The agent's goal is to determine a policy that maps states to actions, such that the cumulative reward is maximized over time. RL algorithms can be divided into two main categories: value-based methods and policy-based methods. Value-based methods focus on estimating the expected return, i.e., the expected cumulative reward, for each state or state action pair, and using this information to determine the optimal policy. Policy-based methods, on the other hand, directly optimize the policy, rather than relying on value estimates. One of the earliest and most well-known value-based methods is Q-learning, which estimates the expected return for each state action pair. The Q value for a state action pair is updated based on the observed reward and the maximum expected return for the next state. The policy is then derived from the Q values, such that the action with the highest Q value is selected in each state. Another popular value-based method is SARSA, State Action Reward State Action, which is similar to Q-learning but updates the Q values based on the expected return for the next action, rather than the maximum expected return. SARSA has the advantage of being able to handle non-stationary environments, where the transition probabilities or reward function can change over time. Policy-based methods directly optimize the policy, rather than relying on value estimates. One example of a policy-based method is reinforce, which uses a parameterized policy and updates the parameters based on the observed rewards. Reinforce has the advantage of being able to handle stochastic policies, where the action selected in a given state is determined by a probability distribution. Another example of a policy-based method is actor-critic, which combines value-based and policy-based methods. The actor network is used to determine the policy, while the critic network is used to estimate the value of the policy. The actor network is updated based on the gradient of the expected return with respect to the policy parameters, while the critic network is updated based on the difference between the estimated value and the observed return. RL algorithms can also be extended to handle continuous action spaces, where the action is a continuous value rather than a discrete value. One example of an RL algorithm for continuous action spaces is Deep Deterministic Policy Gradients, DDPG, which is a variant of actor-critic that uses deep neural networks for both the actor and critic. DDPG has been successfully applied to a variety of control problems, including robotics and autonomous vehicles. RL algorithms can also be extended to handle multi-agent environments, where multiple agents are interacting with each other in the environment. One example of an RL algorithm for multi-agent environments is multi-agent reinforce, which extends reinforce to handle multiple agents by using a decentralized policy and a centralized reward. Another example is the independent Q-learning algorithm, which separates the Q values for each agent, such that each agent only updates its own Q values. RL algorithms have been successfully applied to a variety of problems, including control, game playing, and robotics. For example, RL algorithms have been used to control robots in complex environments, such as robots that can walk, fly, or swim. RL algorithms have also been used to play games, such as chess, Go, and video games, with impressive results. In these applications, the agent learns to play the game by exploring its environment and receiving rewards based on its performance. One of the key advantages of RL is that it can handle complex and dynamic environments, where the reward function and transition probabilities are not known in advance. This allows the agent to learn from its experiences and adapt to changing conditions, which is particularly useful in real-world applications where the environment is often unpredictable. However, there are also several challenges associated with RL. One of the main challenges is the exploration-exploitation trade-off, where the agent must balance the need to explore its environment in order to learn, with the need to exploit its current knowledge in order to maximize its rewards. This can be difficult to balance, especially in large and complex environments, where the agent must make a large number of decisions in order to learn effectively. Another challenge is the sample efficiency of RL algorithms, which refers to the amount of experience needed to learn an optimal policy. RL algorithms typically require a large number of interactions with the environment in order to learn effectively, which can be time-consuming and computationally expensive. This is especially true for problems with high-dimensional state spaces or continuous action spaces. Finally, RL algorithms can also be sensitive to the choice of hyperparameters, such as the learning rate, discount factor, and exploration strategy. Improperly tuning these hyperparameters can lead to suboptimal performance, or even failure to learn a useful policy. Despite these challenges, RL has been making rapid progress in recent years, with new algorithms and techniques being developed to address these challenges and make RL more accessible to a wider range of applications. For example, advances in deep reinforcement learning have enabled the use of deep neural networks to represent the policy and value functions, which has greatly improved the sample efficiency of RL algorithms. In conclusion, reinforcement learning is a powerful and versatile machine learning technique that has been successfully applied to a wide range of problems, including control, game playing, and robotics. Despite the challenges associated with RL, advances in the field are making it increasingly accessible and useful for real-world applications. As the field continues to evolve, it is likely that RL will play an increasingly important role in the development of intelligent systems. Thank you for watching our video. We hope you enjoyed it. As a reminder, please don't forget to subscribe, like, and leave a comment on the video. Your support and engagement helps us continue to create high-quality content using artificial intelligence. We appreciate your interest in our work and look forward to connecting with you in the future. See you in the future.